In this video, I'll talk about Heisenberg's uncertainty entropy at 0K. Heisenberg's uncertainty principle states that delta P times delta X is always greater than h over 4 pi. Delta P is the uncertainty of momentum. Delta X is the uncertainty of position. H is the Planck constant. For electron, the mass is 9 times 10 to the power of negative 31 kilogram. Therefore, delta V times delta X for electron is greater than 6 times 10 to the power of negative 5 meters squared per second. If the uncertainty of the position of electron is 6 nanometers, the uncertainty of its velocity is greater than 10 kilometers per second or 6 miles per second. Therefore, we conclude that any electron has some sort of uncertainty even at 0K. That means an electron must have some positive entropy at 0K. Again, we have this Heisenberg's uncertainty principle. Delta P times delta X is greater than h over 4 pi. For an electron, delta V times delta X is greater than this value. We know the speed of an electron cannot exceed the speed of light. Therefore, the uncertainty of the momentum of the electron cannot be greater than 2 times the speed of light. And we can plug in this value here. We conclude delta X must be greater than 10 to the power of negative 13 meters. The uncertainty of the position of any electron must be greater than 0.1 picometer or 0.001 angstroms. How do we quantify the entropy of electron even at 0K? Based on Heisenberg's uncertainty principle, we need to define a new type of entropy, differential entropy, or you can say continuous entropy. Let's look at this equation. In information theory, entropy is simply negative sum probability times the logarithm of probability. In differential entropy, we need to replace probability with probability density and sum with integral. That's it. So what is probability density? I'll give you one example. If we know a particle is confined in a space of a volume like 100 cubic meters, then the average probability density is 100% divided by the volume of the space, which is 100% divided by 100 cubic meters. Now, what if we know a particle is confined between point A and point B? Then its probability density is 1 over B minus A. So this is 100% divided by the range over here. And we plug in this expression. Fx equals 1 over B minus A over here, and over here we get the differential entropy. The logarithm of B minus A, the logarithm of the range. Nets are equivalent to bits. They just differ by the natural logarithm of 2. We can also compute the differential entropy for other types of functions. Gaussian function here, exponential function, and some more complicated functions. We have corresponding differential entropy. Now we're going to talk about this uncertainty entropy in general. There's another uncertainty principle. Delta E times delta T is greater than h over 4 pi. So what does that mean? Well, within a very short time period, for example 5 times 10 to the power of negative 44 seconds, the uncertainty of the measurement of energy will be 10 to the power of 9 joules or a billion joules. Alright, so we can plug in this value here, and then we can compute delta E. It's going to be greater than 1 billion joules. Because thermodynamic entropy is a measure of energy dispersal, and we have such a large uncertainty associated with energy. Therefore, the oscillations of energy and entropy are wild within such a short time period. However, these oscillations of energy and entropy will average out over a much longer time period.